we were looking at this model reactions. This is basically 3 reactions, A plus A, the forward reaction having a rate constant Kf giving A star plus A, and the third reaction is A star, which is of course it has a backward reaction. There is a second reaction which is a reverse of the first one. The third reaction is A star giving products with a rate constant of Kf prime, the second one having a rate constant Kb. So we could write these rate equations for the production rates of net production rates of species A and A star like this. And of course what you can do now is, okay, we have 2 equations in Ca and Ca star, dCA over dt and dCA star over dt. So let us try to see if we can try to eliminate anything to do with A star. Therefore we now write from the first equation Ca star in terms of Ca and dCA over dt, and then you plug that back in the equation for dCA star over dt wherever Ca star appears, and then you get a complicated looking expression that involves again only dCA over dt and Ca wherever it shows up. So one possibility for us is to now plug back 3 and 4 into 1, okay, and so wherever you have a Ca star you can now plug this over here, and then what happens is you can get a very ugly looking equation in dCA over dt in terms of Ca, right. So plug one and 2 to get an equation relating dCA over dt to Ca. This is going to be a nonlinear second order ODE, right. It's a very highly nonlinear second order ODE, so you're going to have trouble solving that, okay. So not easy to solve. So the alternate approach is the steady state approximation. This is a simplifying approach, so this is a simplifying approach there, that is we now say dCA star over dt is approximately equal to 0. The moment you say that, so we are now essentially trying to adopt the steady state approximation and say dCA star over dt, you should probably say this is quasi steady state. This is quasi steady, it's not really steady, but it's kind of like freeze frame a particular situation that's intermediate where the concentration of the intermediate is apparently not changing, okay, it changes sort of slowly there in this intermediate region. So it's sort of like a quasi steady state approximation rather than just steady state alone. So if you now try to say that this is what we want to apply, call this equation 5, and so what this means is A star is produced quickly in the first reversible reaction and consumed slowly, right. So the moment you have A hitting A molecules hitting each other, you produce A star all right, but its consumption with A in the backward reaction as well as its decomposition to form the products is relatively slow. In that case then you now are producing a lot of A star, but for a while it is there with a certain concentration that does not change a lot, therefore we can now say on a quasi steady basis this is approximately 0. Then so using 5 and 2, if you now apply 5 to 2, go back here, right, and say dC A star over dt is approximately equal to 0, we get Ca star equal to Kf Ca squared divided by Kb Ca plus Kf prime. Not very difficult to figure that. Just have to pull out Ca star wherever it appears, set this equal to 0 on the left hand side, so you can collect terms together and do this. Now let us call this 6 and substitute 6 in 1, the first equation, to get let us say minus dCA over dt equal to omega A, the reaction rate based on A, that is equal to Kf Ca squared divided by Kb divided by Kf prime Ca plus 1. Okay, so we got something, we got an answer there for dCA over dt. So what we have done basically is we now have an expression for Ca star from 6 which we plug in here, and then you can rearrange because you now have a Ca squared there, and then you have a you can plug in over here, and then you should be able to get your dCA over dt, right. So what you are getting basically is Kf Ca squared divided by Kb divided by Kf prime Ca plus 1. Okay, so what is this, where does this take us? Okay, what is our original aim? We wanted to find out if this reaction set of 3 reactions will it behave like a first order reaction or a second order reaction or whatever, okay, as far as like a global reaction is concerned. So the global reaction is A giving products, but A star is like an intermediate, right, that is showing up in a 3-step reaction scheme. And how do you now look at how the global behavior of the rate of depletion of A is going to depend on the concentration of A? That is essentially the global question, and the global question is, is it going to be a first order or a second order? And now you have an expression, you see it is not so obvious. We are now having some soup of an expression there with Ca squared showing up in the numerator and Ca showing up in the denominator. Okay, if you didn't have the plus 1, right, you could have cancelled Ca top and bottom, and you will have the rate depend only on Ca alone, not Ca squared, right. But if you didn't have this term and you had only 1 in the denominator, then you can say that dCA over dt is going to depend on Ca squared. So in the first case you would have deduced that it's going to be a first order reaction. In the second case you would have deduced that it's going to be a second order reaction. So depending upon whether it's going to be first order or second order, what you will have to look for is how does this compare with unity. That is the reason why we have rearranged things like that. It is always good to compare things with 1, okay, to say whether it is going to be much larger than 1 or much smaller than 1. Yeah. So if it is going to be much larger than 1, we ignore 1, if it's going to be much larger than 1, then I'm sorry, I said the same thing. If it is going to be much larger than 1, we ignore 1. If it's going to be much smaller than 1, you ignore it, right? So that's exactly what we're going to do. So at originally we said that this is going to be the fast and this is going to be slow. So with this in mind, we can now look at when would you have which condition as far as this term comparison in comparison with unity. So at high pressure, KB Ca over Kf prime is much greater than 1. Okay, so what you're saying is Kf prime is a unimolecular reaction. Okay, so it's going to go more as P, whereas this is the reverse reaction. The competition is now between, look at basically what's going on. The KFCA squared is coming from producing A star with this forward reaction, the first forward reaction. The KB CA is coming from the reverse reaction, okay, where A star is getting consumed, and the KF prime is actually coming from this one, the third reaction that is also consuming. So essentially, in order for us to understand whether this is going to be larger than 1 or smaller than 1, much larger than 1 or much smaller than 1, we are essentially looking at how the competition between the two reactions that are consuming A star, okay, fare in relation to the one that is producing A star. So there is one reaction that is producing A star, there are two reactions that are consuming A star. So between the two reactions that are consuming A star, there is a competition on which one is doing a better job of consuming than the other. Okay, how is that competition faring when compared to the production rate? That's what this entire expression is all about. So if you want to now look at how this competition in the consumption is happening, you have to understand that this reaction, the backward reaction that is consuming A star, is a bimolecular reaction, which is going to go as P squared, yeah, whereas this third reaction that is consuming A star is a unimolecular reaction, which is going to go as P as for its reaction rate. Therefore, at high pressure, you would expect that the backward reaction, which is the second reaction, is going to predominate over the third reaction that is unimolecular, and therefore we now expect that the numerator in this case is going to be larger than the denominator. Okay, therefore we expect that this should be much larger than 1, and therefore if you now plug that there, then omega A then approximately becomes, you just go back and get rid of the 1, okay, in favor of this expression, and so you now have a KF prime divided by KB, alright, and then the CA gets cancelled with one of the two CA's in the numerator to get only one CA. This will behave like a first order. Alright. At low pressure, right, when the pressure is low, then the square of the pressure will be lower than the pressure raised to 1. Okay, that's what is meant by low, right? So when you now say at low pressure, you have the other situation, which is KB CA over KF prime is much less than 1. Then therefore omega A, so what you do is you drop the complete expression there in comparison with 1, and therefore you now simply get this is equal to KFCA squared, right. So this is second order. So with just applying the steady state approximation, we should now be able to understand how the pressure behavior is going to happen when you are looking at two competing consumption reactions of the intermediates of different molecularities, which will behave differently at different pressures. This is essentially what you are trying to do. That's like a summary of what's going on. Good. Then let's now try to see how this works in the case of the HBr example. The HBr example. Now let's look at the global reaction. The global reaction, H2 plus Br2 gives K twice HBr, right? If this were a molecular level reaction, then what would you say for the rate, the reaction rate? You would say the reaction rate would be dCHBr divided by dt is equal to, we still have to have the nu double prime minus nu single prime. For HBr, nu double prime is 2, nu single prime is 0 for HBr. So you will have twice, yeah, K CH2 times CBr2. That means they will be the concentrations will be raised to powers 1 each, right, if this were a molecular level reaction. So if this were a we would write dCHBr divided by dt equal to twice K CH2 CBr2, but this is wrong. Why is it wrong? It's because it doesn't happen at the molecular level, not because of what we wrote, right? This doesn't happen, this is not what is observed, this is not what is observed. That means if you were to do an experiment where you had hydrogen and bromine and you now allowed the reaction to happen, you now started sampling hydrogen bromide, okay, at different times, you do not find that the rate of change of hydrogen bromide concentration to go linearly as concentration of hydrogen or concentration of bromine as you now do this experiment with varying concentrations of hydrogen or bromine. This is how you would deduce this. You actually find that the rate of change of concentration of bromine is not going linearly as concentrations of hydrogen and bromine. So in reality, yeah. So experiments indicate the following result. dCHBr divided by dt is some constant C1 CH2 CBr2 to the half, right? Well, you know now that that's not the whole story because we now have this bar, but as it is, we are now finding that the rate of production of hydrogen bromide is dependent on the concentration of bromine to the half rather than linearly, right? But that's not the whole story. Hold your breath, this is getting a lot more interesting. So we now have CHBr divided by another constant C2. Well, let's use capital C's here for these constants because we are using small c's for the concentration. So this is so just in case you are getting confused, we will now have this little serif font. So this is C1 and this is C2 CBR2. Oof, what does that mean? This is a pretty wacky expression there. Okay, now if you were to be so intelligent as to immediately start thinking about what we did here, right, the moment you see a 1 plus something, you're like going to say, ah, I know what to do. Okay, I'm going to look at when will this be actually much larger than 1, okay, and then throw away the 1, and then I'm going to rearrange things, and what's going to happen? So you're now going to say, well, this constant times CBR2 is going to go up there, and then it's going to become 1.5. It's not going to become like 1. That was bad. So the original prediction was bad still. Okay, but that's not the most interesting thing. The most interesting thing here is you now have a CHBR in the denominator. Is that okay? What would you allow? What would you want to keep in your final expressions for the production of the production rate of the product? The answer is like what an experimentalist would do, which is you have to allow for the concentrations of stable species that is participating in the reaction, and the stable species would be either reactants or products as well. And here we now find that the concentration of the product is showing up as influencing the rate of production of the product itself. And how? It's showing up in the denominator, right? What does that mean? It means that if you now have a increase in the concentration of HBr, the rate of production of HBr is going to decrease. You started out with no HBr, you started out with only hydrogen and bromine, and you started producing HBr. So the moment you start producing HBr, you are now going to actually impede the reaction, because the rate of production of HBr is going to come down because the concentrations of HBr is increasing. That's what is called a self-inhibiting reaction. Okay, so this is an example of what's called as a self-inhibiting, right? That is, the more the product is produced, well, if you were not scientists, if we were like advertising managers or something, we would probably say the more the product is produced, the less the product is produced. Okay, that's not what we should say. The more the product is produced, the less the rate at which it is produced. Okay, so we are now looking at how the rate of its production is affected by how much of it is produced. So the more the product is produced, the less its rate of production becomes. Right. Now our problem is not just trying to reconcile a self-inhibiting reaction. Our problem is more basic. If I were to say that the actual experimental data were to show that the rate of production of HBr depended on the concentration of bromine power half instead of 1, or 1.5. So the other possibility that I didn't talk about is, what if this entire thing were actually much less than 1? Then you still have the concentration of the rate of production of bromine to be depending upon the concentration of bromine to the half, which is not the case as what the global reaction says, right? So you have a half or 3 halves depending upon this is much greater than 1 or much less than 1. That's like the overall dependence. If it is comparable to 1, you have to keep this as it is, and we can't resolve exactly between half and 3 halves, it is somewhere in between, right, for the concentration of bromine depending influencing the rate. And on top of it we have to explain the presence of CHBr. So how would you do this, right? So this is possible, the above result can be explained by the following 5-step mechanism, right. When we say 5-step mechanism, we are now talking about things are happening at the molecular level. So far this was a global reaction that was not happening at the molecular level, clearly, because if it were, this would be the rate equation, but that is not what is found in the experiments. So something else is happening at the molecular level. Let us look at the 5-step mechanism. So if you now say there was some compound X prime, some species X prime that bromine collided with to form 2Br, that is an intermediate, right, with a rate constant K1, and let us call this reaction 1. This is a chain initiation step, and the intermediate Br now attacks the stable reactant H2 to produce HBr plus another intermediate H, which has a rate constant K2, and let us call this reaction 2. This is a chain propagation step, because we started with a intermediate, reacted with a stable reactant, produced a stable product, but produced another intermediate. So like the net gain and loss of intermediates is the same, okay. So it is just propagating the chain, and let us say we have a third reaction where H is reacting with Br2 to give you HBr plus Br. This is the Br counterpart of H in the previous reaction. So this is, let us say, reaction number 3. This is also a chain propagation step, and then we have H plus HBr that gives you H2 plus Br, right. Look at what is going on, right. This is starting with a intermediate, it is reacting with a stable product and producing a stable reactant and producing another intermediate. So it is intermediate neutral. If you just count intermediates blindly, this is still like a chain propagation step, alright, but it is actually consuming a stable product and producing a stable reactant. That's simply because this is actually the reverse of reaction 2. So you have reversible reactions that are happening, okay, in trying to get into equilibrium under the given conditions, right, and what is the flip side of that? Some of the stable products that you produce might actually get consumed, right. So in this case we found that A plus A, those are the stable reactants, produces A star plus A, right. We are actually not producing any more reactants than we consumed, stable reactants. We have instead produced intermediates, that is alright, okay, that is like a chain initiation step. And the reverse reaction, A plus A star, gives 2A, that is again producing stable reactants. It's kind of like saying, yeah, I started with reactants and then did a lot of things and then got the reactants back. Okay, so the story obviously is not over there. You now have A star giving products. Now let us suppose that this was actually a reverse reaction. Then you would be consuming products to give you intermediates, and that's when you will start looking at self-inhibiting reactions. So when you are having the stable products being involved in reverse reactions, right, then they get consumed and their concentrations affect your global reaction rate, right. So this is a 4 all right, but this is a chain propagating step, all right, but this is the one that is reverse of this is an inhibition reaction, reverse of 2, okay, and finally we now have X prime plus Br plus Br gives, of course the previous reaction had a rate constant K4 and this is a rate constant K5, Br2 plus X prime. Okay, now what's going on here, we are starting with an intermediate, 2 intermediates as a matter of fact, and then producing a stable species. The stable species, so we are actually killing the intermediates, but this way of killing intermediates is to actually produce back the stable reactant. Yeah, so this is a chain terminating step, and it's a reverse of 1. So you are having 2 reverse reactions in this out of 5. So effectively this is having a reverse here, this is having a reverse here, this is the one that is not having a reverse reaction. Yeah, and there are two reactions that are producing HBr, there is one that is consuming HBr, alright, and finally something that you have to keenly note, you now have a termolecular reaction here. So the moment you have a termolecular reaction as opposed to anything else that is bimolecular, okay, the first thing that you have to think about immediately is effective pressure. So anytime you see a unimolecular reaction versus a bimolecular reaction, or a bimolecular reaction versus a termolecular reaction, whenever you are making these kinds of comparisons, the first thing that hits your head is pressure. What's the effective pressure? Okay, so that's one of the things that we will have to be looking at, just like how we did previously for this example. So the answer is, I'm not going to work out the details, that's going to be a homework for you. So here is the answer on how. So what you do, you now take each of those reactions, write the rate equation for whatever is its chief products, okay, in terms of its reactants concentration. This is a molecular level thing, so law of mass action directly applies, right, and we can show using steady state approximation that capital C1 that we had before, right, in the global reaction rate expression is twice K2 times K1 divided by K5 to the half, and C2 equal to K3 divided by K4. So this is a homework for you. So whenever I say we can show, I basically mean you can show. Okay, so just go ahead and show yourself. Don't let's not worry about this. So you understand, right? That means if you now write out the rate equations for each of these and then pick out those rates that are based on intermediates, that is dCbr over dt or dCh over dt. Typically these are the two intermediates that are happening here. Okay, and then set them approximately equal to 0, you now get two equations and you have to try to eliminate CH and CBr in this expression, and you have to pray to all the gods that Cx prime would vanish as well. Alright, and then you will get something that looks like this after massaging all the remaining equations and so on. Okay, don't over massage here because whenever you know the answer you try to fit it in, but I have done this when I was a student. Okay, so it's not terribly bad. You can show this. Yeah. So what else can we do? So this is an example of how the steady state approximation looks like. So now let's look at another approach where we try to simplify, which is called the partial equilibrium. Partial equilibrium approximation. Yeah. Partial equilibrium approximation. Now this is a bit different from what we have done for the steady state approximation, but effectively leads to the same idea. The idea here is we want to try to get algebraic expressions for concentrations of intermediates as a function of concentrations of stable species, does not have to be reactants. Okay, so this is our goal. We do not want to deal with a ODE for the concentration of intermediates. We do not want to deal with a expression there for dC A star over dt and then do a time integration of that and try to find out how the A star changes in time and so on. Okay, so previously we said no change in time. Okay, approximately 0 for the rate, and we just go with a algebraic expression. Is there another way by which we can obtain algebraic expressions for the concentrations of intermediates as a function of concentrations of the stable species, reactants or products, right? The answer is we will now try another approach. Remember, these are based on some physics. It's not like we are trying to do this just for the sake of getting these algebraic expressions. Okay, the previous case we said the intermediates are quickly produced and then they are there as a pool for some time when they are getting interchanged through the chain propagation steps, right, and takes a while for them to happen, and during this time their concentrations are approximately constant. Okay, so that was the physics there. There is another thing that we can try to exploit, which is the occurrence of these reverse reactions to forward reactions, right. So typically when you now have two reactions that are forward and reverse pair, and let us suppose that they are fast, okay, like the first example that we had, no, A plus A gives A star plus A forward and backwards, and that's fast, and the second reaction A star giving products was the one that was slow. So what happens there? You now start with A bombards with itself, like one molecule of A bombards with another molecule of A and quickly produces A star. You now have an equilibrium that is established with A star and A like a soup, and now A star is around and it's in equilibrium with A, right, and it just slowly gets consumed during the third reaction for it to produce the final stable products, right. So during this time, is it possible for us to exploit the equilibrium between A star and A, between the forward and the backward reactions? So if it is now, so effectively what we are looking for is, if you now have fast reactions that are forward and reverse, is it possible to actually apply equilibrium equation rather than rate equation? The rate equation is the one which has a dC A star over dt equals a function of Ca and Ca star. Okay, that is an ODE, and we do not like the ODE, we want an algebraic expression. But the equilibrium equation for that, assuming that it is actually in equilibrium, right, would be, you now have a Kp or a Kc that is equal to concentrations of reactants of the forward reaction divided by concentrations of the reactants of the reverse reaction raised to their respective stoichiometric coefficients, right. That is an algebraic relationship. We don't have a differential equation there, right. So this is essentially what you are trying to do. So here where forward and let us say fast forward and reverse, this is not fast forward, this is fast forward and reverse, okay. Reactions occur so that they could be considered as in equilibrium. Actually we are saying something about their rates. It is not just that they are fast and therefore those reactions are in equilibrium. Essentially when you say something is in equilibrium, we are saying that the forward reaction rate is equal to the backward reaction rate, the reverse reaction rate, okay. So we are basically saying, let us not worry about how fast it is, it is all fast, okay, so they are all equal, right. That is exactly what you are saying here. So and this leads to algebraic relations for intermediate concentration in terms of stable species, okay, using the equilibrium constant. So now you have the equilibrium constant, we know is a ratio of the forward to the backward reaction rates, rate constants, okay. So many times we find these kinds of ratios showing up, you see. So here as well we find these kinds of ratios that are showing up. K1 over K5 for example is actually ratio of forward to backward, right. So that is exactly the equilibrium constant. So we will simply be dealing with equilibrium constant instead of the ratio of the forward and backward reactions, as if the two were in equilibrium. So let us now look at an example. So example, or shouldn't say example, let us say, let us look at, consider template reactions. Template reactions, let us say A plus B2 gives let us say this is forward and backward, so we call this AB plus B, this is KF1, this is KB1, alright, and let us call this 1, and B plus A2 gives and takes AB plus A, and we call this KF2, Kb2, let's call this reaction 2, and AB plus A2 gives and takes A2B plus A, right. And let's have rate constants Kf3 and Kb3, we will call this reaction 3, and finally let's have A plus AB plus M gives A2B plus M, that is reaction 4. That means the last reaction is not a reverse reaction, so or forward, it does not have a reverse reaction. So strictly speaking, the way you should look at it is this is actually 2 reactions, 2 reactions, 2 reactions and 1 reaction, so totally it is actually 7 reactions. It is sort of like having 5 reactions, but if you were to write it like this, it would have been only 3 reactions. This and this going together is forward and reverse, this and this going together is forward and reverse, and the last one, right. So it is just a different way of writing this, and so let us call the rate constant for the fourth one as Kf4. We do not have a Kb4, yeah. So all we are interested in now, it depends on how you are. I mean, if you are like a chemistry kind of person, like I want to see reality, what is this A and B, okay, they are not really happening in reality. You might want to throw hydrogen for A and oxygen for B, okay, and finally you might be looking for H2O, right, and then you can say AB is OH and so on. So essentially what is going on is now you have a atomic species colliding with a molecular species to give rise to 2 atomic species. So this is like a chain branching, right, and this is again starting with 1 intermediate, and this is supposed to be a stable species. You are now getting 2 intermediates, so chain branching, and this is a stable species here, this is an intermediate, this is the final product, and that is an intermediate. So that is a chain propagation. You started with an intermediate, reacting with a stable reactant, producing a stable product and leaving another intermediate, and M is any third body, okay, and you are finally getting a stable product. So this is like a chain termination step. So you can see the sequence of events that happen that starts with the chain initiation, branching, propagation, termination and so on. Now what we are interested in is to find out what is the net rate of production of the final product and how it depends on the concentrations of the stable reactants, and the presence of the intermediates is spoiling the show. We want to try to get rid of them, yeah. So what we want to do then is we say here we say Kf1 Ca Cb2 equal to Kb1 Cab Cb, right, that is for the first reaction, okay, or since you have the same molecularity on either side, okay, this will go as p squared, this will go as p squared. So concentrations can be written in terms of mole fractions, and mole fractions can have pressures, the total pressure, so the pressure dependence is going to be the same on both sides. So it does not matter whether you use a equilibrium constant based on pressure or equilibrium constant based on concentration. I am just going to go back and use concentration equilibrium constants based on pressures, okay. So this simply means that we now have Cab Cb divided by Ca CB2 equal to capital P1, right, capital K subscript P1. Capital K represents equilibrium constant based on pressure, and we have subscript 1 to denote this is actually the equilibrium for the first reaction. Similarly, we can write for the second and third, we can write CAB CA divided by CB CA2 equal to KP2, and the third one CA2B CA equal to, sorry, divided by CAB CA2 equal to KP3. Right. So what was the purpose now? Do we still understand? We want to try to get rid of CB and CA in favor of and CAB as well. We want to get rid of CB, CAB and CA in favor of CB2, CA2 and CA2B. Alright, so this is something that we will do next class.